I'll check if everything's okay. Yes, perfect. So, well, hello everybody. Thanks again, Tamis, for accepting to make a presentation for this fifth session of Oceanics webinar series. So today, Tamis Sapsis will talk about extreme events in fluid flows and water waves for the prediction and statistical quantification problem. So, okay, I think we are fine. So I leave you the floor, Tamis, for the presentation.
Thank you, Maxime, for organizing this. This is wonderful, and thank you for inviting me. So I want to give a quick overview of our work over the last few years on extreme events in complex systems, in particular fluid flows and water waves. So just a quick motivation. Extreme events in engineering science, right? They're very important, especially when we deal with very complex structures. Here you see an offshore platform, right? It's a multi-billion investment, and you see how the waves, operate here. And well, we have to be able to design these structures to survive, if you want, even big storms that for which we don't know exactly, the exact wave profiles. But nevertheless, we have to deal with this type of uncertainty. Other problems involves ship rolling, as you can see here on the right, or accelerations of small vehicles. And here you see a very fast vehicle. It goes to accelerations up to 8 Gs. On the same time, we have problems in flow separation, right? Where again, intermittent flow separation can cause stall, can cause lift reduction, and this is an undesirable effect. At the same time, we have extreme events in nature. Here you see a big flooding event, New York City, 2012, because of a hurricane and the associated surge. And of course, rock waves in the ocean, right? So before I start with the main presentation, I want to make an informal distinction between extreme events and rare events. Okay, so first of all, let's understand what is an extreme event. Extreme event, of course, we define something that is a large deviation from normality, right? And as I said, there are two. Two classes, at least that the way I will describe them. On the one hand, we have the rare event. A rare event doesn't have any specific properties, just a low probability event, like winning the lottery, right? Nothing particular with this specific combination of numbers, just a combination of numbers. Very low probability though. On the other hand, we have extreme events, and I see extreme events as the synergistic action between low probability events and dynamics, right? So in other words, there is a dynamical mechanism that is operating or coexists with the uncertainty. And of course, these are events that live in the tail, and this is what we are after. Okay, some other known mechanisms for extreme events that our framework, will be able to cover, but we will not be focusing on. Slow fast systems, right, where we have a slow manifold, and then we have these jumps, intermittent jumps. Noise-induced instabilities, where the idea is that you have multiple equilibria, and the noise induces transitions, rapid transitions between the two. Very similar to that is also homoclinic, heteroclinic cycles, only that in this case you have a special structure, right, connecting things. The problem is that these are nice setups, of course, but they are not covering the general case that we want to consider. And this is the situation where we have a high dimensional attractor with a lot of uncertainty, and this is the shaded region that you see here. And again, think of this as a very high dimensional region. And then on the same hand, you have these islands these green islands of instability, these can be low dimensional, in fact, and whenever our system is visiting those, you undergo through a nonlinear instability resulting in extreme event. So this is the setup that you see on the bottom right. This is the general setup we will be considering. So I will be focusing on two main problems. The first is associated with a prediction problem, where the question is what type of observables one should track, if you want, in order to be able to say that an extreme event is prominent, is very probable in the near future. And in other words, we want to identify triggers of extremes. And this is obviously important for decision making, for control, for all these type of things. And the second challenge is the statistical quantification problem. And although there are several techniques, and we will discuss a few of those, like large deviations theory, right? Very popular and very important. There are several limitations related to those. Number one, the optimization problems related to large deviations theory is so expensive that it's more or less impossible to solve for the type of problems we're interested in. And number two, we want the full PDF, right? We don't just want the tail of the PDF. So we will see a machine learning approach, a new machine learning approach based on active learning that allows us to do all this with a much simpler, or well, not simpler, but smaller, definitely, subset of simulations. So some motivation, I will talk about rock waves, right? Rock waves in the ocean. Here you see an airplane taking off from an aircraft carrier. You see that the surrounding seas, as I run the movie, you see on the background, the surrounding seas, they're not that bad in the sense that there's no wave breaking. And as the plane takes off, out of nowhere, big wave, right? Essentially, well, the plane made it in this case only because it used propellers, it was not a jet, and that essentially made a big difference in this case. But beyond that, you see that this wave appears really out of nowhere, and these decks, we're talking about 40 to 60 feet high, like more or less close to 15 to 20 meters, right? So these are the type of things we are interested to predict. And I mean, in this case, we will see that there is this so-called modified nonlinear Schrödinger equation that governs things. Essentially, we have like a physical mechanism, a very quick description of the physical mechanism. We have wave groups for a narrow banded spectrum. We have wave groups that propagate with different speeds depending on their size and their length. And then we have this sort of dispersion creates mixing of different wave packets, right? Because they propagate with different speeds, and that mixing may lead to the formation or to the conditions that trigger nonlinear instabilities, right? So here you see a case where you have wave groups that, I mean, on their own, they don't do much. When they combine, they form a wave group that is non-linearly unstable, and that leads to an extreme event. And this type of nonlinear behavior is very nicely seen by doing simulations where you can observe the bold line, which is the known Gaussian tail, right? Describing the wave elevation, while on the same time, you have Gaussian theory for all the wave groups that propagate linearly. We will also see systems related to turbulence. Here you see a situation where the extreme event is with respect to the dissipation rate. And again, while most of the time, this chaotic trajectory that you observe on the upper left, it gives you something that is close to 0.1, the dissipation rate. There are these extreme fluctuations that you can see one here, but also it's demonstrated nicely through the PDF, right? Of the, so to say, PDF of the dissipation rate. So again, the goal is to see if we can predict this type of extreme events. Um, so we formulate the problem as follows. We have some governing equations. K of u is the divergence-free constraint for incompressibility. We assume some initial condition, u naught. We define or we select, if you want, some observable, I. This is an observable from the solution space to some real number. And of course, the goal for us is to identify initial states that trigger this type of extreme events, right? So one can do this, of course, with large deviations theory, but there are several obstacles, right? Well, let's quickly review large deviations theory. Obviously, introduced and studied very thoroughly by Varadan in the 60s. What is the idea? We specify a maximum value for the observables that we're interested in, okay? And then we want to find among all the states that um, 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 that give this type of or surpass this type of critical value, we want to find the one that has the maximum probability. Okay, so think of it as follows. This is the shaded region on the right. It gives us the probability of a particular state. The contours, which are hard to find, of course, they give us the maximum value of the observable associated with each of those initial conditions. What we basically need to do is first to solve this optimization problem, right? Among a specific contour, we want to find the point associated with the maximum probability. Now, this is a hard problem. Why? Because you have to explore a very high dimensional space. In general, the space of initial conditions or the space of states are very high dimensional. And this is an expensive problem to solve. On the other hand, it has been designed for a Gaussian core. Recently, it has been extended for non-Gaussian cases. But this is an important limitation, especially if we want to do things analytically. But most importantly, as I said, we have to search the whole space of initial conditions, and this is a tough problem. Instead, what we do here is something different. We specify within the shaded region, we specify a probability contour. In other words, in the set of initial conditions that have a specific frequency of occurrence or specific probability. And this is less expensive. It's actually very computationally efficient to do, or very cheap if you want. What you basically need to do is to obtain second order statistics for your system, which you can do through some short simulations. And from the second order statistics, you apply a Gaussian assumption. And based on this, you can obtain the set of initial conditions with specific probability. And then along this low dimensional contour, which, by the way, it doesn't have to be Gaussian, but we can make this assumption if we want. So within this low dimensional contour, we can apply optimization techniques to identify the initial conditions associated with the maximum growth. So we first specify the frequency of occurrence, and then along this subset, which is much lower dimensional, you identify the initial condition with the highest growth. This is well defined in the mathematical sense. It's a well-defined problem. It always has a solution. It's a compact subset of the original space. And I mean, if we do that for wave groups, we basically first characterize the growth rate. We do that in the context of nonlinear Schrödinger equation, modified nonlinear Schrödinger equation. We do that with a reduced order model, but of course we could also run the full MNLS for a set of wave groups. These are the type of wave groups that allows us to parameterize the state of the system. It's a two-dimensional state. Here you see the growth, right? This is the maximum amplitude in time divided by A naught. And this is with respect to the initial length of the wave group and the initial amplitude. You see that most of the time, especially in the lower amplitude, initial amplitude regime, there is no growth, right? It's dark blue, which means that this ratio is equal to 1. But after you increase a naught and with sufficiently large L, you can get into very intense growth. Now the question is, from these wave groups that you see here, which of those are likely to occur, right? So we have to, this is one side of the coin, we have to combine this with the spectral information from the spectrum using a scale selection algorithm. We can transform the information from the spectrum into information about the probability of wave groups appearing due to just linear dispersion with a certain amplitude and length scale, right? And this is the feasibility constraint. This is what I was talking about. This is we fixed. And then along this line, this contour, we identify the wave group with a maximum growth, nonlinear growth, right? So it's here. And then we focus, we formulate a trigger or a precursor, if you want, that essentially measures the energy over this particular length scale. The right thing, mathematical thing to do that is a wavelet, right? So we pick this particular wavelet, and from a full wave field, we identify only this wavelet coefficient, and this is what we use to do prediction, right? Nothing else. We don't solve any equation. So here you see the wave groups colored according to this wavelet coefficient. Green wave groups are associated with low probability, yellow is medium, red is high. And sure enough, you see a wave group, which at least by the eye norm, it doesn't look that much different from the others, but our wavelet coefficient analysis is telling us that there will be an extreme event in the future. So here at this point, we are very confident for an extreme event for this particular wave group. And indeed, as time evolves, very quickly, actually, this is several time periods. And I mean, in physical time, this is around 5 to 10 minutes, right? You get an extreme event. We have applied these ideas in experimental data sets. I'm not going to go through those in the sake of time. I want to present one little example before we move on to the second problem, the uncertainty quantification and the tails. This is about predicting bursts of kinetic energy in a channel flow. This is the so-called minimal flow unit. The idea is that you have a turbulent channel flow, 3D simulation, right? And what happens is that for this particular regime, it has been shown in the past by Jimenez and Moyne that the flow can become, can laminarize intermittently, right? So you see that all the vertical structures essentially disappear. Kinetic energy increases rapidly when this happens. And then right after that, flow becomes totally unstable and you have severe generation of kinetic energy and associated dissipation, right? So this is the type of events we want to predict. We apply the similar idea. Again, this is a problem where large deviations, it's extremely hard, right? You cannot apply large deviation in this type of thing because the initial conditions is huge, like to explore the full space. Instead, what we do, we first do a POD analysis and we consider 30 POD modes. And we do that so that we concentrate or we focus in a set of initial states in this ellipsoid of defined by these 30 modes that has a realistic probability to occur. Immediately, the problem dimensionality drops significantly, right, from essentially infinite dimensions to 30. And then within this ball, within this ellipsoid, we solve an optimization problem to identify the initial state with the strongest finite time growth, right? By doing that, we come up with this optimal initial state. And the distance now in this 30-dimensional space of our current state from this optimal state is what is used as a precursor for extreme events. Now, interestingly, this optimal initial state for extreme events, it has, if you compare it with with the mean profile, it has the deficit, velocity deficit exactly at the regions that you see here, which, by the way, they happen to agree with observations made by Jimenez and Pinelli 23 years ago, where they observed that if you force the flow in this particular region, then you can completely get rid of the extreme events. So this is in consistency with this observation that indeed the precursor lives exactly here, which is also what we find. Now we can do a demonstration for this prediction. Red is the probability for an extreme event based on our precursor. Blue is the actual kinetic energy of the flow, and the flow is shown on the right. So at this point, you see that we came close, but we never really reached critical threshold. Here, we predict an extreme event, right? You see the kinetic energy, it's still low. And then, oops, let me move that forward. And then, sure enough, the kinetic, like the flow starts to laminarize. At this point, we have extreme laminarization, and right after that, extreme dissipation rates, right? So again, the question is how you identify this precursor. Now, let me clarify something, that the precursor I presented, although we solve an adjoint set of equations constrained within this hyperellipsoid, this has nothing to do with the solutions that people find in transition theory, right? We are not linearizing, or we are not solving for optimal perturbation around the transition point. Instead, we have an approximation, a rough approximation of the full attractor, and we focus our attention there. So this is what I wanted to cover regarding precursors of extreme events. We have done recently more work where we formulate this as a Bayesian optimization problem, and that gives even nicer results, even for more complicated problems like flow separation in really turbulent regimes. Reynolds close to 10,000. But I will not spend too much time about that. I want to move to the second problem, which is a statistical quantification problem. And the idea, as I said here, is to be able to quantify the tails of the statistics, or the tails of the PDF of any quantity of interest with a very small number of samples that are selected carefully. So now this has important implications. When I say that we select samples carefully, it means that I implicitly assume that we have a black box where we can run it with any type of initial conditions or parameters and get an accurate answer. So this is the assumption here that we have an expensive black box, right? This can be a climate simulator, or it can be a simulation for the flow around the ship or an offshore platform. So it's assumed to be accurate, but also very expensive. And so we cannot use techniques like randomized sampling, right? Smart randomized sampling based on Markov chain, Monte Carlo, for example, or similar techniques. We want to do things. We want to find the tails with like 20 to 30 simulations at most. This is what we can afford. So very quickly, for the problem formulation, as I said, we have a dynamical system, right? We assume that this is expensive. Theta, U is the state of the system. High dimensional theta is the parameter vector, random parameter vector for which we have the probability density function, right? This can be thought as moderate dimensionality, right? 20, 30, this type of thing. Obviously not thousands, but not one or two. And the goal is to estimate the PDF for any type of observable Q that is a function of the state U, or you can think it as a map from theta of omega, the random vector, to Q, right? So this map T is expensive. We have to run the black box. We have to solve these equations. So the idea is to find the statistics of Q with the minimum number of computations of T. right? This is the idea. And we are going to set up the problem as an active learning problem, but with a twist, right? Because if you do active learning, you will focus with standard acquisition functions, you will focus on the main mass of the distribution. Here, we're interested for the tails, we're interested for the extreme events. So we assume that we are given n-1 experiments. In other words, we have done already n-1 experiments, theta 1, theta 2, theta n-1. The question is, what should be theta n so that we can efficiently estimate the probability density function f of t, which is the PDF of the observable. We do a Gaussian, we set up a Gaussian cross regression scheme, right, from the parameter to observation map from theta to t. This is what you see here, right? So on the diagram, you see this is supposed to be the real map, like the exact map, t of theta. This is the regression, right? T bar of using the n-1 samples. And together with that, we have this confidence bounds, right? Which is Tn-1 plus sigma, n minus sigma. And from there, of course, if we have the estimation for T bar, we can obtain, in principle, an estimation for the PDF, right? It's simple. We use the Gaussian cross regression, we use the statistics of theta. We can obtain a sequence of PDFs. The question is, how do we choose the next sample, though, right? So this is how we do it. We assume a hypothetical new point, and if we add a hypothetical new point to our data set, let's say here, theta star, then obviously the mean prediction doesn't change, right? The blue line remains the same because we don't want to run the full experiment. So the best guess we can have about the outcome of this theta star is just from the Gaussian cross regression model. But what changes, though, are the confidence bounds, right? So the confidence bound here vanish. So we will utilize this and we will obtain two bound sequences. We call them bound PDFs. Essentially, these are the PDFs obtained from the two confidence bounds, right? So it's the PDF for the map T bar, the estimation, plus 1 sigma gives us a PDF, and the T bar minus sigma. Obviously, these are easily computed because they involve only the surrogate, the Gaussian cross regression scheme. Now, if we have excellent, sampling, these two bounds, like these two bound PDFs, should be very close to each other, right? And now this is important because we don't really need to sample all the theta space. We don't really need even to get T bar accurate everywhere, just only in regions that essentially make this F converge to each other, right? These two sequences. So this is what we are going to do. And in this way, we formulate this acquisition function or selection criterion. It's the theta star that minimize the distance between the logarithms of these two bound PDFs, right? And you see that I employ the distance of the logarithms and not the KL distance because I want to emphasize the tails. This is what I'm after. If I multiply here with f of t, which would be the standard thing to do for library divergence, I would actually lose emphasis from the extreme events, from the rare events. So this is the optimization problem we solve initially. That is a paper that came out 3 years ago. And it turns out that this is an expensive problem, but the selection of, expensive optimization problem, but the selection of this theta does not depend obviously on the actual value. So that's good. And we also have proven consistency, right? Now, as I said, this is good, but it is an expensive optimization problem to solve. So to avoid this issue, we obtained an asymptotic form of this criterion where we added a little parameter beta here to essentially consider bound sequences that are associated with the map T plus beta times sigma n, where beta is a free parameter, and we can select it arbitrarily. So we choose beta to be very, very small. And in this case, the criterion through an asymptotic argument takes this form here that you see. And I don't want to spend too much time. I only want to say that this criterion that you see here, which is the asymptotic form of the original criterion, can essentially be bounded by this nice expression that you see on the right. So this criterion is bounded by this expression, which is what? It's the error from the Gaussian process regression weighted according to the probability density function of the input parameters theta, but very important. So what you have in the numerator is essentially the integrated variance reduction in the active learning literature. So the important difference, though, is that we have naturally this term appearing in the denominator, which is the probability density function of the estimated output. So what this does is that it emphasizes the tails, it emphasizes the extreme events. The good news is that this criterion that you have on the right is actually very efficient to compute and optimize. You can write its gradient analytically, so we can apply this to very high dimensional problems like theta can live in 30 to 40 dimensions. Essentially, the limitation comes from the operation of the good operation of Gaussian process regression, which is close to 50 dimensions, more or less. Let me demonstrate this in a simple nonlinear oscillator example. So here is the oscillator. Nonlinear, as I said, the PDF that we are essentially targeting is what you see on the right. The right-hand side is expanded into a Caron-Lev expansion, and we maintain two terms just for demonstration purposes. As I said, the quantity of interest is the maximum of the response, and this is how the PDF should look at the end. And that's the map, right? This is the exact map with respect to theta 1 and theta 2. So we apply this idea. We start with 4 samples, and we apply 4 more samples using the algorithm I mentioned. This is the PDF, exact and prediction. Dashed line is the one standard deviation. So, and obviously 8 samples are not enough. After 20 iterations, well, you see that first of all, the samples are very non-trivial the way they're selected. And the PDF has started to converge, and we're talking about 10 standard deviations, more or less, right, from 0. After 30 iterations, after 70 iterations, we have a spot-on agreement between the two PDFs in the logarithmic scale. And this is the sampling pattern, right, in the theta space. You see that it's a mix of samples in the core associated with approximating the core of the PDF, but also for extreme events, as you can see here. We have done the same analysis for a much higher dimensional input space. So here you see results for 30 dimensional theta, and the dashed lines are criteria from active learning literature, the standard criteria, integrated variance reduction or uncertainty sampling, and this is how the sampling happens in this case. While the likelihood weighted, as we call them, the criteria with this extra term in the denominator that arises naturally, they manage to obtain, much better properties. I want to emphasize here that what you see is the logarithm of the error, where the error is defined as the L1 of the L1 of the logarithms of the PDFs, right? So it's logarithm of the logarithm. That's really a very tough metric if you want. So the difference that you see here is essentially at least 1 order of magnitude improvement. On the left, you see noiseless observations, and the difference is way more pronounced if you have noisy observations. We have applied this. Let me see. I will show very quickly one more example, just because it's fancier. So we have applied this on to simulate an offshore platform in random waves. We use a smooth particle hydrodynamics code to do the simulation. This is, if you want, an artificial wave tank. By the way, you can do this in the wave tank, right? There is no limitations. The quantity of interest is the maximum force and the maximum moment acting on the structure. We consider Johnson spectrum. And again, this is how the force converges. That's the PDF. We start with 4 samples, and then after 16 samples, we have good agreement, essentially 2 to 3 standard deviations away from the mean. You see some of the samples are associated with the tail region, some with the core. Similar idea for the moment. Again, after 15 iterations, we are able to capture very nicely the PDF. This is what I want you to cover. To very briefly summarize, I've talked about 2 things. One is to track the precursor, which is like to identify characteristic signals that precede extreme events. And then the other problem is to how to cleverly select data instead of just relying on big data, because in many problems we don't have the luxury to simulate big data. Where we have developed a new acquisition function that allows us to do that very effectively. Just a minor comment that recently we have managed to use the idea of this new acquisition function for general Bayesian optimization problems, and that allowed us to revisit essentially the track the precursor problem using Bayesian optimization techniques, and this is definitely a very promising approach. Thank you very much for your attention. I hope I'm not over time, but yeah, I'm happy to take any questions.
Yes, thanks, Semis. No, I think we are just right on time. So thanks again. I don't know if someone have any questions. I don't see any question in the chat.
Maybe Maxime, I have a question regarding, can you hear me?
Yes.
Okay, perfect. Hi, Semis.
I see.
Okay. And maybe I have a question regarding the first aspect for extreme prediction. I didn't pretty much get how do you specify the contour in your technique. Can you?
Yes, elaborate. Yeah, sure. So the contour there, you assume that you have second order statistics.
Mm-hmm.
And after you have, or anyway, some samples, after you have second order statistics, the contour is essentially a hyperellipsoid, using the covariance matrix. It's nothing.
So you compute it basically from maybe samples that you have, you compute the covariance and you get the ellipse from the covariance, and this is your
exactly.
Okay.
Exactly. Like for the water waves example I showed there, you still rely on second order statistics, but you do this exercise for the absolute value of the amplitude. I'm sorry,
Yes, yes.
This is the one, right? So you don't see a Gaussian here.
Sure.
It's just a Rayleigh type of thing, right?
Okay.
But this is very inexpensive to compute because you don't need a nonlinear model. You just take random realizations of the wave group, of the wave field using, let's say, a random phase model, and from there you can compute the PDF of A and L. This is really quick to do, again, because you don't really need a model that resolves the nonlinearity.
Okay, thank you. And maybe a naive question, but what is the lead time of you predicting extremes? Is it do you predict extremes as they start occurring, or do you do it with your observables maybe a little bit before?
Yes. Let me, I mean, I skip all this in the interest of time, but I will show you, demonstrate, like for the water waves, it's much earlier. It is exactly at the moment the instability is triggered, but at that time, the extreme event is nowhere even close to find it. So here you see the predictor and the actual extreme event. The extreme event is zeta of t, and the predictor is lambda of t, right? And this is the extreme event.
Yes.
And this is when the precursor actually is activated. If you want actual numbers for the turbulence problem, we're talking about 3 times of the turnover time scale, the eddy turnover time. So this is more or less even actually bigger than the largest Lyapunov exponent.
Yeah, it's impressive, exactly. Yeah.
Yes, so because the reason actually we can get away with the largest Lyapunov exponent is simply because the extreme events are not dominated by this exponent; they are dominated by a different instability, and this instability is slower to grow. Similar things can be said for the water waves. Here I'm showing some experimental results with Amin Chub and Miguel Honorato, who provides experimental data. And again, the prediction time is, think of the time in the period of the wave is close to 1 second, and we're talking to 16 time units. Lead time. Of course, you can change that. You can increase that, but your false negatives and false positives, will grow in this case. Yes.
Thank you, Demis.
Of course, I see a question in the chat. Yes, for the optimization problem, how do we practically solve it? For up until in 2018, when we had this nasty optimization problem here, yeah, we were using swarm particles, something very expensive. But since last year, for this new acquisition function that you see on the right, we use gradient optimization techniques with random restarts, and that's very efficient, it works very good.
Thanks, Demis. It's first order optimization or second order?
This is first order optimization.
Okay, thanks.
Yes. And again, like the important thing here, we could use, we could actually compute, second derivatives and use second order. But I think it's more important in this case to have even a rough estimation, of what input samples are the informative ones. This makes things converge significantly faster.
Okay, thanks. Is there any other questions? I might have one, maybe it's a naive question also, but I think it was on slide 44 regarding one of your applications.
Yep.
Yeah, so maybe it's not this one, but the previous one, I don't remember exactly.
You remember?
Maybe again 42. Sorry, I don't see the number on my screen. It's when you displayed the optimal sampling, the first map for the optimal sampling. Maybe it's just after that.
Okay, I think that's the one, 44, right? This is the.
Yeah, I don't. Yeah, but I remember that you told us that you have some samples obviously located in the extremes and also other samples in the middle of the map. I was wondering if there is a reason for these points to be in the middle of the map and not in the border, since the value seems to be quite the same. Is there a reason or
right?
Not?
Let me tell you. So you probably talk about this picture.
Yes,
right?
yes, exactly.
Okay, good. So here we want to specify this map Tn of theta, right, with high accuracy. It turns out that in the center, it's where your theta has the highest probability.
Okay.
So think of theta 1 and theta 2, it follows a Gaussian distribution that is centered. And on the other hand, the yellow and dark blue, dark yellow and dark blue, they are the regions that gives you high outputs.
Yeah.
So what eventually happens is that you have a balance between sampling the high probability thetas, because these contribute to the core of the distribution. If you don't get the core right, you will never get the distribution right. And then you also want to be accurate in regions associated with extreme events, because that gives you the tail right.
Okay.
That's how you end up with a lot of samples close to highly probable thetas and a lot of samples close to high or large expected values of t.
Yeah, okay, thanks.
That's the idea.
Yeah, that's clear, thanks.
And if you want, this is one of the successes of this criterion, that is able to do that, you know, without tuning anything, without any parameters. It is sequentially, and it is jumping. Like, it's not that it's covering one region and then it goes to the other.
Yes.
It uniformly samples across this, you know, this area that you see here.
Okay, so basically, if you want to have more sample again, you will not get stuck, but have more sample in this diagonal.
Exactly. You don't get stuck, because by design, if you, like, let's say, if you end up with really low, if you sample, you know, particular neighborhood, then the error goes down, and then the criterion is has no, like, it has no weight, no emphasis there. So it will definitely go somewhere else.
Yeah.
And asymptotically, it's correct. So even if you sample this domain here, this area, very accurately, then you will start expanding, you know, in more irrelevant regions.
Okay.
And yeah, this is, you want, compared with other techniques that aim to sample the input space, like active subspace methods. The problem with active subspace methods is that you have to truncate the input space. So asymptotically, you will never be correct. Here we don't, truncate anything. We progressively converge to the exact thing.
Okay, thanks. So that's clear. Is there any other question from the audience? I have to go from my side, but is there any other question? I guess Said can lead the discussion from now. But if there is no other questions, I can also end the session. So just don't hesitate if you have another question.
Yeah, if you have other questions, you can also email me. I'm happy to, you know, to share any material that you want, like with additional information. Okay, thanks. And you have no problem with sharing the video of the webinar? No? Okay. Yep. This is great. Okay. And if you can just send me the slides also, if it's not a problem, so I can... No, it's no problem. Okay. Don't think that it's a big file, that's all. Yes, yes, with a video, I guess, but I will download it and make it available through the Oceanics website. Sure. With Ronan, yes. Okay. Yep. Okay, great. So if no other questions, thanks again, Themis. Thank you, Maxime, for the invitation. Yes. And again, we can still keep in touch, especially when Ronan will be back from holidays. Absolutely, absolutely. Perfect. Take care, everyone. Thanks again. Thanks, everyone, for attending to this webinar. Bye-bye. Bye. Bye-bye. Bye-bye.